press the bell icon on the YouTube app and never miss another update.
Today we are going to discuss part 9 of the chapter Oscillation in first PUC Physics. Now in the previous class we have discussed about two important concepts. One, period of oscillation of combination of springs as well as period of oscillation when a spring is connected to two masses. At the same time, we have derived the expression for period of oscillation of a simple pendulum, right? And we obtained that T is equal to, right, 2 pi into square root of L by G. So now let us discuss some important points regarding the oscillation of simple pendulum. We know that we have period of oscillation of simple pendulum. Period of oscillation of simple pendulum T is equal to 2 pi into square root of L by G, where L is the length of the pendulum, that is the distance between the point of suspension and the center of gravity of the bob, and G is acceleration due to gravity at that place, right? Now where L is length of pendulum and G acceleration due to gravity at the place, acceleration due to gravity at the place. Here one important thing is, for a given simple pendulum, when we suspend a bob from a point through an inextensible string, length remains the same, right? Now what about this acceleration due to gravity? This acceleration due to gravity is constant only at a given place, right? It is different at different places on the surface of the earth, because we know that variation of acceleration due to gravity, right, with latitude, that is from place to place, it is maximum at poles and minimum at equator. Again, acceleration due to gravity is maximum, right, that is 9.8 meter per second on surface of earth, right, at certain place. With increasing the height or altitude, acceleration due to gravity decreases. As we move towards the center of the earth, that is the width depth, acceleration due to gravity decreases. Suppose from place to place, if the same simple pendulum is taken from one place to another place, right, now in that particular case this period depends upon acceleration due to gravity, right? Now number one will take, right, now that period of simple pendulum T is directly proportional to square root of, right, length of the pendulum, right? With increase in length of the pendulum, period of oscillation increases. So when the length is increased by n times, time period increases by square root of n times. So if T1 and T2 are the time periods of two pendulums at a given place having the length L1 and L2, then T1 by T2 is equal to square root of L1 by L2. Now Number 2, right, acceleration due to gravity, mean period t depends on, right, g at that place. This is the third point. Second point. Now the third point is that now we are having a seconds pendulum. Seconds pendulum is that simple pendulum whose period of oscillation is equal to 2 seconds, right? So now period of oscillation of seconds pendulum, right, is t is equal to 2 seconds. A simple pendulum having the period of oscillation is equal to 2 seconds is called a seconds pendulum. Now here now another point here, we know that to describe an event or a motion or a phenomena we need a reference point, right? Generally we take a Cartesian coordinate system or spherical system or cylindrical system as a frame of reference, right? A frame of reference may be inertial frame of reference and it may be a non-inertial frame of reference. All inertial frames are either at rest with respect to a fixed point or they are moving with uniform velocity. That means their acceleration is 0. A non-inertial frame of reference is one, right, which is in accelerated motion, right? So any frame of reference which is moving with certain acceleration is a non-inertial frame of reference, right? Let us take an example of a car, right? Now somebody, right, in some car they will suspend a doll or they will suspend the disc, right, CD disc, like that. So it acts as a pendulum, simple pendulum, and it began to oscillate when it set into oscillation. But when we observe the period of oscillation, when car is at rest or car is moving with uniform velocity, the period remains the same depending upon its length. But when the car is speeding up or slowing down, its period will be different from that one. Why it happens? Because while speeding up or speeding down, the car acts as a non-inertial frame of reference. While at rest or moving with uniform velocity, it acts as inertial frame of reference. Now let us see what is the period of oscillation of a simple pendulum if it is in a non-inertial frame of rest. We can imagine that, right? A doll which is suspended in a car and the speed of the car is increasing with certain acceleration, right? Now in a non-inertial frame of reference, non-inertial frame of reference, right, moving with an acceleration, say A, right? Now here let us take, this is the rigid support through which, right, the pendulum is suspended. Now this, right, top or the plane to which the simple pendulum is suspended is moving with an acceleration a. Now when we consider the bob of the simple pendulum, here now the acceleration due to gravity acts vertically downwards. Now we will take in that is in more correct to say horizontal plane. Now the frame of reference is moving in horizontal plane. Now this is the acceleration of the frame of reference. Now the bob is subjected to two acceleration. One downward acceleration due to gravity and perpendicular to which in horizontal direction acceleration of the frame of reference. Now since we know that these two are the vectors, now the net acceleration due to gravity, right, acting on the bob is that g dash, and the g dash is the resultant of g and a. We know that this is equal to g square plus a square. Now this is the length of the pendulum. So in this case, the period of oscillation t is equal to 2 pi into square root of L by g dash, that is equal to 2 pi into square root of L by square root of g square plus a square. This is the period of oscillation, right? Now from this one, as acceleration is more, increases, then the value of g dash decreases, right? Then period of oscillation increases. That means to say, in a non-inertial frame, right, the period is less. In inertial frame, period is more, right, for a given simple pendulum, right. Now we take another case here. Right. Suppose fifth one we'll take it here only. Now the fifth point, what we are considering, period of oscillation of a simple pendulum in a lift or elevator. What happens to the period of simple pendulum, right, in a lift? Now generally the lift may be in four conditions: at rest, inertial frame, moving upwards or downwards with uniform speed, right, again it is an inertial frame, right. Suppose if the lift is moving upwards or downwards with certain acceleration, either speeding up or speeding down, right, then it becomes a non-inertial frame of reference. Then the period of oscillation will change, right. Now first we will take the case, right, when lift is at rest or moving upwards or downwards with uniform speed, right. That means acceleration A of the lift is equal to 0, right. Here we can take the lift, this is an elevator, right. Now we are having a simple pendulum here with length L. Here this acceleration A is equal to 0. Now there is only the acceleration is acceleration due to gravity, right? So lift is at rest or moving upward or downward with uniform speed, right? Clear? Then in this case the effective acceleration due to gravity is equal to g, right? Therefore T is equal to 2 pi into square root of L by g, right? The period of oscillation remains the same if the lift is at rest or moving upward or downward with the uniform, right, speed, right? Now when the lift is moving upwards, right, B. When the lift is moving upwards with an acceleration A, with an acceleration A, then let us take a lift here. Now a simple pendulum, right? Now G is acting downwards. If the right body, lift is moving upwards, then it is having an acceleration E. There is a force called fictitious force or pseudo force acting on the bob, right, in a vertically upward direction, right? Now this, not this one, sorry, the lift is moving in vertically upward direction, but the acceleration, right, due to the pseudo force is acting in downward direction. Here this is F is equal to ma, that is the pseudo force. That pseudo force is acting in downward direction. Now in this case that G dash is equal to G plus A, right? Now in this case the period of oscillation T is equal to 2 pi into square root of L by G plus A, right? That means here if the lift is moving vertically upwards with a certain acceleration, the time period decreases. Time period, right, gets decreased here. Now we will take C. When the lift is moving downwards, when the lift is moving downwards with an acceleration A, now when the lift is moving with an acceleration a pseudo force is acting on the bob, right, but in the opposite direction of the acceleration of the lift, right? Therefore in this case, right, the effective acceleration due to gravity, because see it, when lift is moving upwards, both G and A are in downward direction, they get added, G plus E. But when the lift is moving downwards, right, the acceleration of pseudo force is acting vertically upward direction. G is acting vertically downward direction. Now G dash is equal to G minus A here. It is for the same reason when we are moving in a lift, right? Moving in a lift. When the lift is just starts moving upwards, we feel a jerk because of that pseudo force. When lift is moving up with an acceleration, our weight is equal to m into G plus A. When the lift is moving downwards with acceleration, our weight is equal to m into g minus a. Here, when lift is moving upwards, our weight appears to be increased. When lift is moving downwards or with acceleration, our weight is appears to be decreased, right? That is called apparent loss of weight, and the effective weight is called apparent weight. The same thing happens when we are moving in a giant wheel. When we are moving in the giant wheel in upward direction, right? Now our weight is m into g plus a. Increase in weight, right, does not affect us, right? Now, when the person is moving from top to bottom of the giant wheel, then he feels loss of weight, right? And that fears him. He tries to hold something to maintain the weight. He needs the support to maintain his weight, right? So, therefore, he feels weightlessness, right? Not weightlessness exactly said. He feels there is a decrease in its weight, right? And that feeling make the people to shout or cry or anything, etc. It is nothing but a pseudo force, right? In amusement park, the same force we say it is a thrill, right? Now, this T is equal to 2 pi into square root of L by G minus A. Now D, when lift is in free fall. What do you mean by free fall? Suppose if we are having a cable here, that cable is broken up. When the lift is in free fall, now it starts, right, moving with an acceleration which is equal to g. Now the time period t is equal to 2 pi into, right, square root of L by C g minus g, right? G minus g is equal to 0, right? Now the time period becomes infinity. The time period becomes infinity means frequency is equal to 1 by t is equal to 0. Frequency is equal to 1 by t is equal to 0 means the number of oscillations executed per second is 0. That means the simple pendulum is not vibrating, right? Because its period becomes infinity and frequency becomes 0, right? This is the period of oscillation of a simple pendulum in a lift, right? Remember, in case of, right, lift is moving upwards, effective acceleration due to gravity increases, t decreases. Here the value of t increases. Here it becomes infinity when g is equal to g for free fall. Remember that period is infinity means frequency is 0. Frequency is 0 means there is no oscillation of the pendulum. Right? Now the question is, why simple pendulum does not oscillate under that condition? Because we know that for any particle executing simple harmonic motion or oscillation, a restoring force is needed. Remember, we have the derivation of simple pendulum, that restoring force is equal to minus mg sin theta. A component of the gravitational force provides the necessary restoring force there, right? So under free fall, F is equal to minus m into 0 sin theta, that is equal to 0. That means there is no restoring force. If you displace the simple pendulum from its mean position to somewhere, it remains there. It will not come back. Right, in other words, right, the period becomes infinity and frequency becomes 0. The real reason is that according to equation we say that t becomes infinity and f becomes 0, but the real physics in that is there is no restoring force acting on the bob under that situation, right? Is that clear? Now sixth one we will take. Now period of oscillation of a conical pendulum. Conical pendulum. Suppose we are having a pendulum here, right? Now whenever it is executing simple harmonic motion, it executes to and fro motion, right? It retraces this arc again and again at a regular interval of time. We say that the simple pendulum is oscillating. But you see this one, this is the string, there is a bob here. When it is made in such a way that the bob, right, executes circular motion, right? The bob is executing circular motion, right? Sometimes we all do that, right? Whenever we are having an object tied to a string and one end string is holding, we will do like that only, right? And now that becomes a conical pendulum, right? Because that string moves in the shape of a cone, right? That is called conical pendulum. So if it is a conical pendulum, right, then this bob we are having that executes circular path. This is the bob, this is the length of the bob, this is the angle theta, and the effective length of the bob becomes L cos theta. In this case, that period T is equal to 2 pi into square root of L cos theta by G, where L is original length of the pendulum and theta is the angle by the string of the pendulum with the vertical or initial position of the pendulum, and L cos theta is the effective length of the pendulum here, right? So T is equal to 2 pi into square root of L by cos theta. And another one we are having, right? Now period of oscillation of a bob, of course, of simple pendulum, right? Bob of density rho in a liquid of density, right, D. Suppose we are having this is the density of liquid D. Now we are having a simple pendulum bob density rho. Then the period of oscillation is given by T is equal to 2 pi into square root of L by G into 1 minus D by rho, right, where L is the length of the pendulum, or we can take T is equal to 2 pi into square root of L over G into, right, we take it here, For our convenience, if we get confused with that small d, t is equal to 2 pi into square root of L by G into 1 minus density of the liquid by density of the bomb. It is more easier, right, to remember, right? Clearly, rho L is the density of the liquid in which the bob is oscillating. Rho B is the density of the material of the bob, right? Is that clear? That's all about oscillation of simple pendulum in various cases. Generally, these concepts and formulae will help you in competitive examination, right? We will discuss some more concepts about oscillation of different right systems, right? That we will discuss later at the end of this chapter, right? Because that is help in competitive examination, right? Okay, is that clear? So we have completed that discussion about the oscillation of a simple pendulum by finding the derivation or right period of oscillation of a pendulum, and frequency can be obtained straight away by taking the reciprocal of time period. And we have discussed what are the factors on which, right, acceleration due to gravity, right, depends. You might have asked, what is the period of revolution of pendulum at center of earth, right? I mean core at the center of the earth. At the center of the earth, G is equal to 0. When G is equal to 0, T is equal to infinity, right? So period is infinity, but simple pendulum won't oscillate at the center of the earth. Similarly, there may be a question, what happens to, right, a simple pendulum when it is put it in satellite in vacuum or at a height of 1 kilometer, 10 kilometer, or at a depth of 1 kilometer or some kilometers. So how the period of oscillation changes, right? If we know from place to place what is the change in acceleration, if the acceleration decreases, time period increases, right? If the acceleration due to gravity increases, right? If the if the acceleration due to gravity increases, the time period decreases. If the acceleration due to gravity decreases, the time period increases. That is the simple logic here, right? Remember, with increase in acceleration due to gravity, when we go from one place to another place, period decreases. If there is a decrease in acceleration due to gravity, the period increases, right? Is that clear? That's all about simple pendulum. Now, let us discuss very important concept in simple harmonic motion, that is energy associated with right a particle executing simple harmonic motion, right? Now before going to that, let us recall that, right? Energy of a body is the capacity to do work, right? And work done on a body is equal to the product of force and displacement, right? So energy of a body is the capacity to do work, right? Work is said to be done when energy is spent, right? Now when work is done on a system, generally energy of the system increases. When work is done by the system, generally energy of the system decreases. Here there is a close relation between, right, work done and energy. We know that potential energy of a body, right, at any position, right, is the energy possessed by the body by the virtue of that position, right? So when we consider initial position of a body where potential energy is 0, when we need to change the position of the body, right, we need to apply a force, and applied force produces displacement, and this amount of work done on the body, that appears as potential energy of the body, right? Here there are two types of potential energies, right? Gravitational potential energy and elastic potential energy. Gravitational potential energy arises due to work done against the gravity, right? Remember, let us imagine that a stone lying on the ground, its potential energy is 0. When we lift the stone to certain height, we need to do work against the gravity, and that work done, right, W is equal to, right, force into displacement, that is mg into h. M is mass of the stone, mg is weight of the stone, that is the force needed to apply, right? H is the height, and that is equal to, right, gravitational potential energy. And energy possessed by a body by the virtue of its motion or speed or velocity is, right, kinetic energy. Now the kinetic energy of a body moving with a velocity v is, right, half mv square, where m is velocity, m is mass, v is velocity of the body. Remember that is one thing. Velocity is a vector quantity having both and magnitude and direction. So v square is equal to vector v dot vector v is equal to v square, right? This v square is a scalar. V square is a scalar that we have discussed in vectors, cross product, dot product, right? Characteristics of dot product of vector. Why I am telling here means, here energy is a scalar quantity having only magnitude and no direction at all. But in this expression, when I say that v is velocity, I am telling that v, but the expression does not involve v. Actually it involves v square, right? So v square is the dot product of v, and it is a scalar quantity, right, having only magnitude and no direction at all, because dot product of two vectors, right, is called a scalar product, and it is a scalar, right? So therefore energy is a vector quantity, both potential energy, total energy, right, and kinetic energy, all forms of energy are scalar quantities, right. Now with this little introduction, right, we will take another concept, that is energy of a particle executing simple harmonic motion. Energy of a particle executing simple harmonic motion, right. Now let us consider a simple pendulum, mean position. Suppose we are having a bob here, right. It is having a displacement y, and at that instant of time it is moving with a velocity v, either towards or away from the mean position, that is immaterial, right. Now we see at position p of the bob, right, at that instant, I have taken at that instant of time t, the body is displaced, right. Now it possesses potential energy due to its displacement y from mean position. It possesses potential energy due to displacement from its mean position. The bob also possesses kinetic energy due to its motion or velocity. That means it has both potential energy at p, right. Bob or any particle having simple harmonic motion in general, right, has potential energy and kinetic energy, right. It possesses both potential energy and kinetic energy. And here the total energy is equal to the sum of potential energy and kinetic energy. If we represent total energy of simple harmonic motion is E, then that is equal to EP plus EK. Here EP means potential energy, EK means kinetic energy. So a particle executing simple harmonic motion possesses both potential energy and kinetic energy due to its position from the mean position and the velocity of simple harmonic motion at any instant of time. And of course, total energy is equal to the sum of potential energy and kinetic energy. Now, let us find expression for potential energy, kinetic energy and the total energy of a particle executing simple harmonic motion. Now, expression for potential energy of a particle in simple harmonic motion, that is, we take it as EP. Now, let us consider a particle of mass m executing simple harmonic motion, right. Now, here we will take the case of the simple pendulum, the bob as a particle, Right. Now this is the position of the particle P at any instant of time t. Right. Now let y be displacement of the particle at time t. This is the displacement y. Right. Now the restoring force, right, acting on the particle, right. Now restoring force at time t, right, will take, I am taking this magnitude of restoring force at time t. F is equal to m omega square y. Let us take it as equation number 1, where m is mass of the particle, omega is angular velocity, and y is displacement at that position or at time t. Now, to hold this bob in this position, we need a force. We need a force. Yeah, right. Now, force needed to hold the bob, the particle at y, right, the displacement y, is again F is equal to m omega square y. Right. We need to apply. Now suppose if dy be a small displacement, right, in the particle, right, done by the external force, right, then the amount of work done is dw. If dw is small amount of work done to displace, right, through a small, right, displacement dy, we will take it as dy, then, right, that work done dw is equal to F into dy, or dw is equal to F m omega square y into dy. Let us take it as equation number 3. Now, this dw is the small amount of work done in displacing the particle through a small displacement dy. Now, what is the amount of work done in displacing the particle from the in its mean position, y is equal to 0 to y is equal to v? That amount of work done appears as a potential energy. Therefore, potential energy of the particle executing simple harmonic motion at any instant of time is equal to the total amount of work done in displacing the bob from its mean position to the position at that instant of time. That means we have potential energy is equal to work done to change the position from y is equal to 0 to y is equal to y. Right. Now, this potential energy equal to, now it is integral of work done 0 to w, and remember those concepts once again. In work power energy, work done by a constant force and work done by a variable force. Work done by a constant force is, right, I will write it here, right? Work done is equal to Fs cos theta. It is work done by a constant force, where F is the constant force, right, whose magnitude and direction do not change with time. If it is a variable force, then it is work done is equal to integral of A to B F cos theta, right, into ds, where ds is the small displacement, right, f theta, this is not f cos theta into ds, right. Now here A is the initial position and B is the final position. Now here when the particle is at mean position, y is equal to 0, work done is 0, and when the particle is at displacement y is equal to y, then the work done is equal to w. Here w is the work done, it is equal to EP, right. Now this is integral 0 to dw, that is equal to, so integral of, right, what is dw? M omega square y into dy within the limit y is equal to 0 to y is equal to y. Or now this EP is equal to W is equal to, if we integral that one, so M is constant, omega square is constant taken out. When we integrate y dy, right, we will get y square by 2 within the limit 0 to y, that is equal to m omega square, right. Now applying the limit, y square by 2 when y is equal to y, minus 0 when y is equal to 0, therefore we will get EP is equal to half m omega square y square. Right. This is the potential energy expression for potential energy of a particle executing simple harmonic motion, where m is mass constant for given particle, omega is angular velocity again constant for given simple harmonic motion, and here as the y changes with respect to time, the potential energy also changes with respect to time. We know that in simple harmonic motion, velocity, acceleration and force, they are different at different positions. For example, at mean position, velocity maximum, acceleration 0, force 0. At extreme, velocity 0, acceleration maximum maximum at that point. So here, just like velocity, acceleration of simple harmonic motion and restoring force, right, potential energy also changes with respect to time, right. And remember this equation, right, EP is equal to half m omega square y square, right. Let us conclude at this right point of time. Now the next we will discuss the kinetic energy of simple harmonic motion, total energy, certain important points regarding the energy of simple harmonic motion, right. Okay, thank you very much.